So this lesson will be from chapter 20. This is going to be what we call vectors. This is a really cool topic here that you get into. We're just going to kind of touch on it, but this is really when you start to get into some physics and some really cool math uses as we move into some things here. You also, of course, will see it in, a lot of times, a lot of this will be used in electricity and things like that too. So our objective here is we want to find the magnitude of a vector in standard position given the coordinates of the endpoint. So quantities that we have used so far in the text have been described by specifying their size or magnitude. So magnitude is another word for size. So quantities such as area, volume, length, and temperature, which are characterized by magnitude only. So we call these scalars. So they're only measured by size. Other quantities such as electrical current, force, velocity, acceleration are called vectors. A quantity described by magnitude or length and direction is what we refer to as a vector. So a vector has two things going on. It's going to have magnitude and it's going to have direction. So a vector is going to represent a shift or movement from one point to another. So essentially, a vector is kind of like what in geometry we'd call it the ray. But here, this would be what's called a vector. The length of the vector is called the magnitude. How long it is, what size we're talking about. So in a vector, there's a tail, which is kind of the initial point. And then where the arrow is, this is usually described as the head. So a lot of times we'll have these ordered pairs in here that will help us determine the length. And also we have direction. So remember, direction, if you think about navigation, direction is going to be defined a couple of ways, either by ordered pairs or by what we call an angle measure, degrees and things like that. So vectors are going to be represented, like I said, straight arrows. So again, in geometry, call them rays. We also can call them an arrow. Again, the length of the arrow is going to represent the magnitude of the vector. The symbol for magnitude of the vector is going to be this like double parallel bar V inside there. So the curved arrow shows the counterclockwise direction of the vector. So remember, if we talk about direction, we're talking about angle. So typically, as we kind of said down here, the magnitude is going to be the length, and then we have the beginning point and the end point down here. So we have that kind of going on with this. So notice how we have this vector that starts at what we call standard position on our graph. So standard position on a graph is going to be this 0, 0. That's going to be where the tail is. And then it's going to move out to here, which we call the head, or again, they call it the end point. So this is going to be some type of ordered pair. So the other thing we have going on, so from the length of the vector is going to be the magnitude, and then we need this angle measure. Usually it's going to be in a counterclockwise direction. So from this x-axis here, that rotation is going to help us create what we call the direction of the magnitude. A lot of times, instead of using the x-axis, a lot of things use north as a bearing, and then we veer some type of degree off of north. So keep that in mind. That this will be a little bit different because we're using x and y axis, but in the real world, we'd be using, like north, south, east, and west as our bearings. So to determine the magnitude of a vector in standard position, so when we say standard position, we're talking about putting the vector actually on a graph. So the magnitude of a vector in standard position is going to be the length of the hypotenuse of the right triangle formed by the vector, the x-axis, and the vertical line from the endpoint of the vector to the x-axis. So if I look up here, you notice how we have, let me get rid of this 0, 0. So to find the length of the vector, which is the magnitude. So if we want to find this line right here, that's going to be the magnitude. What we did is the x-axis becomes one side of the right triangle. And if we drop down from the endpoint, the head, this creates our right triangle. And then we have theta would be our included, that would be our acute angle in solving it. So again, to find the vector, it's going to get kind of modified as, the square root of x squared plus y squared. So again, to do this, all we really need to know is the endpoint 1, 1, since we're starting at standard position. So we don't have to deal with two order pairs. We just got to deal with that endpoint, which is going to be defined by an x coordinate and a y coordinate. So to find the magnitude of a vector in standard position, we simply just substitute in to the Pythagorean theorem and do the math. So if we look at this example here, find the magnitude to the nearest tenth. So vector P is the first one we're talking about. So notice that vector P, the coordinates are 4, 3. So it's going to be what they describe as x1, y1. So if I'm doing my vector, I can find the length of that vector by doing the square root of, it's going to be x1 squared plus y1 squared is our formula. So I'm going to have the square root of, and since x1 was the 4, this is going to be 4 squared. And then the y1 is going to be 3 squared. That's going to be, then give me this 16 plus 9. 16 plus 9 is 25. And square root of 25, actually don't need a calculator, that would just be 5. So notice how, if we make a right triangle out of this side here would be 4, and this side here would be 3. So it's interesting that this order pair actually defines the legs of the right triangle. So 4 would be one leg, and 3 would be the other leg. So remember, the legs are used to find what we call the hypotenuse, which is the slanted line. So a lot of times, remember, we use, the formula was, like if I draw a right triangle over here, we'd have a squared plus b squared is equal to c squared in that sense. So each one of these sides, a, b, and c would be defined as the, I don't need these squares necessarily, except when I write the formula, but notice how the a and b are defined as the legs, and c is the hypotenuse in that sense. So let's see what else they have here. So this would be example A. Example B, vector R in figure 20.4. Don't have that one. If the coordinates are -2, -5. So let's just see if I don't know if I made that drawing or not. Oh, here it is. So this would be part B down here. So we want to find the length of this vector. So again, to find the length of this vector, we can use the formula, which is the square root of x1 squared plus y1 squared. So if we know the endpoints of the vector in standard position, we can just substitute those straight in, and this would be -2 squared plus -5 squared. So this is going to be the square root of 4 plus 25, which is going to be the square root of 29. Now that one, we're going to have to use a calculator for. So the square root of 29. If we round to the 10th place, that would be 5.4. So the length of that vector would be approximately 5.4. And I don't think they give us a unit of measurement here. So we just have a 5.4 as its magnitude. So another thing we get into is, like I said, vectors have magnitude and they also have direction. To find the direction of a vector in standard position, given the coordinates of the endpoint, if the vector is in standard position, falls in the quadrant 1, we can use white triangle trigonometry to find the direction of the vector. for a vector in standard position with an endpoint in quadrant 1, the tangent function can be used to find the direction or the angle of the vector. So if it's in quadrant 1, it's fairly straightforward. We're going to be using tangent. So remember, we have so ka toa. So notice how toa is tangent opposite over adjacent. So the tangent of an angle is going to equal the opposite over the adjacent. So remember, the angle's got to be the acute angle. So if we construct a right triangle over here, notice how this is going to be theta here. So notice how this would be 3 and this would be 4. So notice how the y-coordinate is going to be the opposite side and the x-coordinate is going to be the adjacent side. So notice how they say the tangent of theta is going to equal y over x. So the opposite side actually is going to be the y value, and the adjacent side is going to actually be the, so the 3 is going to be the y value, and the 4 is going to be the x value. So notice how the 4 is moving left to right, the 3 is moving up and down. So remember, y is a vertical direction and x is a horizontal direction. So if we substitute into the formula, we're going to have 3 over 4. So remember, to find the angle, we actually have to use the inverse tangent. So the inverse tangent of 3/4 is actually going to give me the angle theta. So theta is going to equal whatever that is. So if I use my calculator, the inverse tangent of 3/4. So second tangent gives me inverse tangent. If we just put 3 divided by 4 in there, close our parenthesis, that should give us our angle. And if we round that to the nearest tenth of a degree, that would be 36.8, 36.9 degrees. So theta would equal then 36.9 degrees. 36.9 degrees. Clean that up a little bit. Make that a little bit neater. So 36.9 degrees. So another thing we got going on is converting vectors in standard position between the rectangular coordinate system notation and a polar coordinate notation. So another coordinate system that is often used with vectors is called the polar coordinate system. In the polar coordinate system, points are in relation to a fixed point called the pole or origin, and the fixed line called the polar axis. So what we have here is, instead of having an x-axis, y-axis, we have just a specific point called the pole or the origin. And then we have this, what's called the polar axis. So notice how that's kind of like a vector. So what happens is this vector is going to be rotating around. So it's going to be kind of rotating on an angle, and the measurement here you'll see is, when we do an example, notice how they have this 345 degrees. That's going to be what we call polar coordinate notation. That's going to be a polar coordinate. So polar coordinate, notice the first number is actually the magnitude of the vector, and then the 45 is the direction of the vector. So like we said, a vector is made up of two things. It's made up of magnitude and it's made up of direction. So polar coordinate actually fits a vector a lot better than rectangular coordinates do. So what we want to do is we want to convert between these types of measurements. So if we give you a rectangular coordinate system, we may want to convert to a polar coordinate system. If we give you a polar coordinate system, we want to maybe have to convert back to a rectangular coordinate system. So a lot of times, like I said, a vector, vector OP, or sometimes we may use this notation right here, vector OP like that. Its coordinates would be then this 3, 45 degrees. So the 3 is actually the magnitude, and the 45 degrees is its direction. So relationships between the rectangular system and the polar coordinate system, if I want to convert from rectangular to polar, so in other words, I'm given an ordered pair. If I give you an ordered pair x, y, what I can do is I can find r, which is kind of the magnitude of the vector, or they call the radius as well. So we have the square root of x squared plus y squared. That looks familiar. That was like magnitude that we did earlier. And to find the angle, the central angle, if you will, we're going to do the inverse tangent of y over x. Because remember, that's going to be our opposite over our adjacent concept. So that's going to give us from rectangular to polar. So remember, polar is going to be this r theta. So r again is like the magnitude. So to find to find the x coordinate, we multiply r times cosine of theta. So in a rectangular coordinate system, if I draw a right triangle, if this is the angle, notice that x is the adjacent side and y is the opposite side. And this would be like your r. So if I do like the cosine of theta, notice that the cosine of theta is going to be x over r. So if I use proportion, notice I can cross multiply. X is going to equal r cosine of theta. Notice that y is actually the opposite side. So by definition, the sine of theta is going to be the opposite over the hypotenuse. In other words, that's going to be y over r. Again, if I cross multiply, we're going to get y equals r sine of theta. So that's where that kind of comes from. So the other thing is, to convert the endpoint of a vector in rectangular notation to polar notation, we have to do this. We have to if I want to find r using the relationship, again, we're going to have r equals the square root of x squared plus y squared. Again, to find theta, we're going to be using the relationship. Then theta is going to equal the inverse tangent of y over r. So we'll have that going on. So see if we can piece this all together. So given the endpoint of a vector in standard position, find its polar coordinates. So let's look at A to start with. Let's just kind of look at some stuff here. I don't know what they did here, but they have like a typo. This should be like y over x down here, not a y over r. These are the same formulas. They just wrote them backwards. Okay. So given the endpoint of a vector in standard position, find the polar coordinates. So let's look at what we have here. So A, if I just draw this out, so I have like 3, 4, so it's 1, 2, 3, 1, 2, 3, 4. So I have a endpoint up here. So what I'm trying to do is find the polar coordinates of this vector. So remember, to do that, I need to find r, and I need to find theta. So for part A, we need to know what r is, and we need to know what theta is. So remember, theta is the central angle, and r is this magnitude or the length of the vector. Or if we think about circles, it could also be called the radius. So that's how we have, if we drop this down, we'd have a right triangle. So notice how this 3 would be the adjacent side and this 4 would be the opposite side, because the r is actually the hypotenuse. So again, if I follow this out here, to find r, we have to use the square root of x squared, which is going to be 3 squared, plus then 4 squared. So that's how it just comes from the Pythagorean theorem. So it's going to be the square root of 9 plus 16. So r is going to equal the square root of 25. So r is going to equal 5. To find theta, we have to use the inverse tangent of y over x. So 4 over 3. And that'll actually give me what the central angle is, or the theta. So we can find that on our calculator. Inverse tangent of 4/3. This gives us then 53.1 degrees. 53.1 degrees. So that'd be part A. So that would be 553.1 degrees would be my polar coordinates. For part B, if I was drawing a picture of this, you'd have 5, 8, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 6, 7, 8. So your endpoint would be up here. So what we're looking for is the polar coordinates that would get us to the same spot. So I would need to know what R is. I would need to know what theta is. Again, if you want to, you can just go ahead and drop this down and make this a right triangle. So that's how this would be a 5 and this would be an 8. So to find R, that's how this order pair was, this 5, 8. So we can just use the formula that says, use the Pythagorean theorem and just use the endpoint, 5 squared plus this 8 squared. So R is going to equal then the square root of 25 plus this 64. So that's going to be what? 89. So R is going to be the square root of 89. Again, you don't have to do any of this math if you don't want to. You can actually put it in at the very beginning as a square root of 5 squared plus 8 squared. But I'm just going to do the square root of 89. So that's going to give us, if I round to the nearest tenth, would be 9.4. So if I want to find theta, we have to use the inverse tangent. Since we know 8 over 5, the R would actually be rounded, so that would not be a good choice to use R. Even though we have R now, we could use that, but let's use the given values, which are the 8 over 5, since the R was actually rounded. So if we do that, theta is going to equal then the inverse tangent of 8/5. That's going to give us 57.99, round that to the 10th place. So that's going to round all the way up to 58.0. So 58.0 degrees, or just 58 degrees. So your polar coordinates would be the R, the radius, or again, magnitude would be 9.4, and the central angle or the direction of the vector would be 58 degrees. So again, if I want to find the endpoint of vector in polar notation, if I want to convert that to rectangular notation, we have these formulas here. So to find the x-coordinate, we use our cosine of theta. And to find the y-coordinate, we use our sine of theta. Our sine of theta. So again, if I drew a picture of this, so the vector itself would be a length of 2, and this angle here would be 30 degrees. What I'm looking for is the height, y, and the horizontal direction, x. So notice that to do that, that would be the opposite over the hypotenuse. So it'd be like the sine of theta, or the sine of 30 degrees equals y over 2. And then I'd have to cross multiply, and that would be y equals 2 sine of theta. I'm sorry, 2 the sine of 30 degrees. But notice how that's essentially what they're doing there is R sine of theta. So I really don't have to do that much work. I can really just go straight here to this formula and just say, hey, x is going to be equal, the R was the 2 times the cosine of theta, and the y is just going to be R sine of theta, well, it's going to be 2 sine of theta. But again, theta was given to us. That's actually 30 degrees. So 2 cosine of 30 degrees and sine of 30 degrees. So if we go ahead and calculate those out, so 2 cosine of 30 degrees, 2 cosine of 30. Remember, my mode is already in degree measure, so this is going to just be fine. So it's going to be like 1.7 would be our x value if I round to the tenths place, 1.7. And our y value would be 2 sine of 30. So 2 sine of 30 degrees. And that gives me 1. So that's a nice clean one. 1. So it means the sine of 30 degrees was actually 1/2. So that's an easier one. So sine of 30 degrees is 1/2. The tangent of 45 degrees is 1. So I'm learning a few of these as we go along. Okay. So some other things we do is we have a calculator that can do some of this. So if I have rectangular coordinates, I'll convert them into polar in degrees. Let's see if we can do this on our calculator. So we have feature rectangular to polar r coordinate. Let's see what we got here. This looks like you got a couple of different formulas here. So this kind of stands from rectangular polar r and polar theta. So let's see here. Let's got to slide this over. So let's see if I want to do this 512. So if we hit second angle, notice that number 7 is polar rx, polar ry. So they say rectangular to polar. So we want rectangular to polar. So rectangular to polar. So if I hit that one, polar r is, looks like we want to put our x value and y value in here. So let's see, 5 comma is, where is the comma on this calculator? There it is, right in front of me, the big 7, 5 comma 12. If I close that out, hit enter, that gives me the 13 for the r. And then if we do second angle, if I do rectangular polar theta, hit that one, and put the coordinates again, and again, 5 comma 12, hit enter. That'll give me the angle of, if I round it to the nearest tenth of a degree, theta would be 67.4 degrees. So 1367.4 degrees. If we want to verify this, are we really doing this right? Or are we just kind of making this stuff up? Well, we actually did the math up here. So we got, for 3, 4, we got 553.1. So if we want to double check that with our answer up here, if we hit second angle, we want to do the rectangular that we want to do, number 5. So the order pair was 3, 4, 3 comma 4. That's supposed to give us our r value, which was 5. That looks good. And if we do second angle rectangular and get our central angle, our direction, again, if we put the 3 comma 4 in, hit enter, that'll give us this 53.1. So yeah, we're doing something right there. Okay. So if I want to do rectangular to, or polar to rectangular, that's going to be this 7 and 8, polar to rectangular. So notice how now we put the r and theta into this thing. So notice how this is in radian measure. So we need to change our mode to radian measure. So if we come in here and get the radian measure, and then quit. So if we go in here and do second angle number 7, this will give us our X value. So hit enter. And if we put the 6 comma pi over 3, now that little pi symbol does come in handy. That should give us our X coordinate, which is going to be 3. And then our Y value, if we hit second angle number 8, and put the polar coordinates in for that, 6 comma alpha pi rather, divided by 3, close parenthesis. That gives me my Y value is not as clean. My Y value is going to be 5.2. So 3, 5.2 would be our coordinates. So again, if I was doing this by hand, we would say our X value is going to be our cosine of pi over 3. And our Y value is going to be our sine of pi over 3. So if I use that, we double check it that way. So if we type in 6 times cosine of pi over 3, divided by 3, that does give me 3. And then if I do 6 sine of pi over 3, two parentheses there. And that should give me this other number of this 5 point, so about 5.2. So that actually allows us to even avoid doing that by hand. We actually do this by the calculator. So I hope you find that useful.